So I'm a structural engineer from Spain originally, but I live in New Zealand. I work at the University of Auckland. I'm going to present today the end of my PhD project, which I submitted in 2019, so it's a little bit old, but there were other priorities after finishing my PhD, and I kind of left columns and moved into diaphragms, which is a much bigger problem. Now, my PhD was about FRP anchors. Most of my work was on FRP anchors, and I ended the PhD developing a design method for these anchors, and I wanted to test if they work in a real structure because it was only component test in the lab. So I decided to do columns. I was working with the local branch of EBR-FRP, and they had problems with this design where they could, confine the columns, and there were provisions in ACI for that, but they didn't know how to improve the moment capacity of columns. So everything I'm going to talk about today or now is earthquakes. Everything in New Zealand is about earthquakes. All of my work is about earthquakes, okay? So no gravity loads. These are not a problem. Now, why do we need anchors? Because if we only have FRP seats and no anchors, the column becomes a rigid body. We concentrate all the cracking at the bottom, and we fracture the back. So we are actually making it worse. We need the FRP anchors into the bottom so we can have that distributed cracking behavior. I built 6 columns, one as built on the left, and then the reinforcement, the dimensions is all constant. And then I tried different things. With the first 3 tests, I wanted to test if I could predict when the anchor was going to fail, and I could. And with the last 2, I wanted to shift the failure mode to the seats to see if I could predict when the seats will fail, and I could. And then I introduced a number of variables. Like the first one didn't have any confinement, the second one did, to see if the compression tension cycle had any difference, the confinement had any effect. Then I increased the number of anchors and their size to have 2 or 3 data points, see if I could really predict those numbers very well. And then I had huge anchors, a lot of them, and less layers of FRP to shift the failure mode. And finally, I introduced a bond-breaking layer. This was kind of improvisation because I was seeing that the push and pull directions were very different, hugely asymmetric behavior. So we introduced that bond-breaking layer at the bottom to try to control the behavior a little bit more, and that worked well. Now, I used just first principles that we know for 50 years, section analysis, moment curvature, the document from ACI and my own FRP anchor research to model these columns. Nothing fancy, no FBA, nothing like that. Then, I just order the steel, build, make the concrete, install the anchors. In case you cannot see them, we install first the first layer of FRP, then the anchors, and then another layer on top. And that's me not looking very happy for some reason. By that time, I was tired of installing FRP. And this is the test setup. We have a beam on top to apply axial load. I think it was 10% axial load ratio. And then lateral load, cyclic load to simulate it. And these are the hysteresis loops. A lot of information in here. Basically, we have column 1 there as built. There was a problem with actuators. I could not go beyond that point, but then it's easy enough to simulate its flexural behavior. So it's easy enough to simulate that, and I did that. And then anchor, 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 and then sheet and sheet failure. So I will walk through this in more detail in the next slide, but basically we have a first point there with the non-linearity start, point, and a point there where the peak load happens. Now, what does that mean? If we try to fit these curves, red is as built, through the typical bilinear behavior, it does not work. We are not reflecting the behavior. We are missing those peaks, we are missing those drops. So basically, we need to find a different model to design the seismic strengthening or flexural strengthening of columns and beams. And the reason for that is there are three stages in this behavior. One, elastic, where there is no damage, basically, only cracking, there is no steel yielding, no FRP debonding, and DIC showing, that one doesn't work very well because it's all the way up here, and I was focusing on the anchorage area. And then that finishes, that point, where the non-linearity starts, whether that is steel yielding or FRP debonding. The FRP debonds here at the bottom, where the moment is higher, and the debond progresses up and we increase the load. Now, because the bar yields more or less at the same strain as the FRP debond, and they are not too far from each other, the load, the moment is similar. So I have kind of put them together in the same volume. From that point on, we have, depending on the test, depending on the properties, amount of FRP and whatnot, either a plateau or a hardening. So the FRP is debonding from the bottom up. The FRP cannot take more strain because if the strain increases, the FRP debonds, we have longer length, and then the phenomena continues until the whole thing is debonded. At that point, the FRP will continue increasing its strength until it cracks, depending on the column, the anchor, or the sheet. Now, we have here column 2, so the anchor fracture. We can see here the little fracture. And at that point is the maximum load. It cannot take any more load from that point on. And it starts dropping. Depending on the test, the anchor will break little by little, or more suddenly, depending on how the configuration of the FRP was. And then the as-built behavior is resumed. So basically, we have this trilinear behavior with an elastic phase determined by the bonding strain, non-linear state, either hardening or plateau, where the peak is determined by the fracture of the FRP. And then, because we don't know if that is going to be a sudden drop or more staggered, I just make it vertical, and the as-built behavior is pressure. Now, the moment capacity, we can calculate it very easily, and it's quite accurate, 6% different, because it's just section analysis. It's just one more material with a different Young model. It's a linear elastic until failure. So we can predict the moment capacity very well. We've been doing this for 70 years, right? The problem comes when we want to calculate the deformation, the lateral drift. Why that? Because all the theories, and now I'm going heavy into seismic, so I apologize if you're not familiar with seismic design. All of the theories are based on steel reinforced concrete. So it does not include not only the FRP properties, but the synergies of how the FRP behaves with the concrete, which is the critical part here, because FRP debonds, and that is an inelastic mechanism. So this theory is plastic hinge theory, right? And it lumps all the plasticity into the plastic hinge length. At the bottom of the column, this is made of strain penetration, the part of the strain in the bar that penetrates into the foundation, and the part on top of the foundation in the column. And that's the equation where we have an elastic component and a plastic component. Now, what I have done, which is not final, so don't go back to your office and start using this, and then blame me when things happen the way they should. Basically, what I have done is assume that there is no plasticity at the top, and it's only strain penetration for top and bottom. Probably not correct, but this is what I can do with the test I have. So basically, I'm saying the plastic hinge length is 2 times the strain penetration. The strain penetration depends on the yield, stress, the diameter of the bar, and this psi factor. I back calculated the psi factor for all of my columns, and I got 0.0116, the coefficient of variation is pretty much 0, that I have 6 tests, 5, that they are all the same. So we will need to repeat this several different sizes, different actual load ratios, different FRP configurations, and everything. So in conclusion, there is no difference with the tension compression cycle, there is no fatigue degradation, there is no effect of the confinement. Why do I know that? Because test 2 and test 3, which were more or less a repeat, they have the same numbers, and I could predict the moment capacity very well. So that means there is no, we are not compromising the strength of the anchor because of that cycle. We have that 3-stage behavior that we have seen in many other applications as well. So we need to change our thinking when we are doing concrete with FRP. The bond breaking layer works very well, but the contractors were not happy. That is something that needs to be negotiated with the contractors beforehand, rather than just write a line in the drawing. And then we don't need anything fancy. We don't need any FPA. We don't need anything like that. Just cross-section analysis, first principle, engineering thinking instead of recipe cooking, and we can get those moment capacities very well. And we need more research for calculating the drift and the displacement. And I accept donations, by the way. And that's all. Thank you very much.